A little bit of introduction of myself. I'm a mathematician, so like half of you probably in this audience. I work on numerical PDEs and scientific computing. So in the past few years, I get my hands really deep in those problems. And what I'm going to show you today is a chain of results that I have done, collaborated with a bunch of people. Ruyu and Gunther are originally from inverse problem community. I really learned a lot from them. Shichen and Zhiyan, they are my students, and Leonardo was borrowed from Ling Li. So I'd like to talk about multiscale inverse problems. So what is inverse problems? If you think about a physical system, let's say this physical system is prescribed by a partial differential equation. And something in this differential equation that is not known to you, and I parameterize this thing by theta. So theta is something that you want to get to know about. You cannot detect theta directly, but rather you can inject some source into the system and take the measurement. So your job is to use the incoming data and the output data to infer for the media. So mathematically, what we do is we define this operator. This operator is parameterized by theta, something that is unknown, but it maps from the input to the output. So the typical forward problem is I tell you the theta, and you tell me this operator, in the sense that for every x given to this operator, you tell me the output. The inverse problem is a reverse process. I tell you the whole map. Can you infer for the parameter theta? So inverse problem typically, after all the theories gets done, you need to implement it numerically, and usually we formulate it into the PDE constraint optimization. So you write down your PDE over here. This L is a PDE operator. It has an unknown parameter theta in it. So you say that I gave you the source, and you solve for the equation with some unknown parameter, and you want to compare the measured data with the true data. So naturally, this PDE constraint optimization, it falls into the category, into the formulation that stochastic gradient descent is very powerful at, because it's a summation of a lot of sub-loss function, and all the sub-loss function, they share the minimizer. Or you can invert this PDE operator directly over here and insert it back. This is unconstrained optimization, but it has the twisted gradient formulation. But nevertheless, this is the inverse problem. Let me give you some very famous examples in the inverse problem community. One thing comes from the seismic imaging. So you have this underneath the lake, you have some tomography that you want to reconstruct. So what you do is you put a ship over here that sends the waves in, and the waves get bounced back from the bottom of the lake, and you put the detectors over here to retrieve the information. So using the incoming source and reflected wave, you try to recover the bottom of the lake. So the associated forward problem is a Helmholtz equation that describes how wave propagates. Usually the forward problem is you solve for this Helmholtz equation. But the inverse problem is I tell you the input wave, you measure the output wave, can you reconstruct the so-called refractive index in the Helmholtz equation? So that's one very typical inverse problem. Another very typical inverse problem is from medical imaging. A person lies on the bed, and we shine the laser light onto this person, and we take the detection at the bottom of the bed, and we use this input light source and the detected light to reconstruct the bone structure of this person. The associated forward problem is the radiative transfer equation as your PDE model. And your job is to use the incoming to the outgoing map. We call it the albedo operator to reconstruct the bone structure, or the optical property in the radiative transfer. So the third inverse problem comes from electrical impedance tomography, or mathematically we call it the Cadron problem. This picture comes from a remote sensing. This is a little bit off. But nevertheless, the forward PDE is an elliptic type equation. The map that you try to reconstruct, the map that is given to you is I tell you the Dirichlet boundary condition, and you take the flux measurement. Can you use the Dirichlet to Norman map to reconstruct the diffusivity coefficient in your equation? So this is another example for inverse problem. But nevertheless, let me summarize a little bit. You have the Helmholtz equation, the radiative transfer equation, or elliptic equation, and all these equations have some unknown parameters that you want to reconstruct. So what you do is you take some measurement, hoping this map can tell you enough information of the media. Okay. So I come into this community. I was not originally from this community. I was an outsider for inverse problem. To me, this was a little bit confusing. So inverse scattering for seismic imaging, or optical tomography for medical imaging, or electrical impedance tomography. So these three are studied separately by different people. But from my point of view, I came from the multiscale PDE analysis. Somehow, Helmholtz equation, radiative transfer equation, elliptic equation, to me, are the same equation, just represented at different scales. So I think it's not a foreign concept for many of us. We have this multi-scale structure in our physical system. From the nanoscale to gradually to the micron or meter scale, you pass from the quantum mechanics to classical mechanics, and classical mechanics to kinetic mechanics, and kinetic mechanics to the continuum mechanics. You have different sets of equations at different regime. At the nanoscale, you have the Schrodinger equation. And you say the Schrodinger equation, the Planck constant is so small, then we pass to the different scale, and we have the Newtonsecond law. And then suppose I have a bunch of particles all together, the Newtonsecond law gets bypassed to the statistical mechanics. Over here, we have the Boltzmann equation. And then you say the Boltzmann equation is to simulate the flow of the fluid. Then we have the Euler and Navier-Stokes equation. So all these equations can be linked from one to another. We can derive the Newton from Schrodinger, derive Boltzmann from Newton, and derive Euler from the Boltzmann. And this is true for other physical systems as well. One example is photons for light propagation. If you think about light, a century ago, great minds told us that light has wave-particle duality. You can never understand light purely from the wave point of view. You can never understand light purely from the particle point of view. You have to use both perspectives. For Maxwell, so light can be understood as the waves, or the Maxwell equation. It's magnetic wave equation. You write down the Maxwell equation, describe light propagation. Or you can say light is particles. If light is regarded as particles, we give it a name called photons, and the dynamics for photons is regarded as a radiative transfer equation. Or we can say we would like to describe the light propagation in this room, and all these lights gives us all these lights are shining, and it's actually a diffusing effect, and we have the diffusion equation. So this phenomena, wave-particle duality, this phenomena makes physicists happy, but somehow makes mathematicians really mad. Hilbert in 1900, he asked the following question. If the underlying physics is the same, how come you have different mathematical description for the same physics? And during the past century, we studied really hard, and eventually we come to the conclusion, maybe the secret lies in the so-called asymptotic analysis. One such explanation comes from Schrodinger to Newton. So Schrodinger equation, for example, you have this small Planck constant. And you Google Planck constant, you get a number that is 10 to minus 34, something like that. And mathematicians see this number, say, oh, it's such a small number, we can probably send it to 0. But if you really look at this number, it is matched with a unit that is kilogram, second, and meter. So those are the units that we human beings sense the world, but not how electrons sense the world. If you rescale to how electrons sense the world, the nanometer, nanosecond, and I don't know how many grams, this is not such a small number. But nevertheless, suppose we forcefully want to assess the dynamics of electron using our mind, using our unit, we do not observe the quantum effect anymore. And in this regime, we can pass from Schrodinger to the Newton. And that's what we would call the the classical or semi-classical limit. And the same story happens from Newton to Boltzmann and Boltzmann to Euler by sending different parameters to 0 or infinity. So mathematically, what we do is we write down an equation. And in this equation, there are some small parameters. And we say this small parameters is so small, we send it to 0. Then mathematically, we typically expand your solution in terms of this epsilon. There's a leading order and first order, etc. And we put this expansion back into this equation and perform the order by order matching. And eventually, we find out that in this limit, this equation is asymptotically equivalent to a different equation. And this holds true if you derive the Newtonsecond law from the Schrodinger. So for the later part of the talk, what I would like to argue is that the Maxwell equation, or the Helmholtz equation as a simplified version of the Maxwell equation, is asymptotically the same as the radiative transfer, which is also asymptotically the same as the diffusion equation. As a consequence, the inverse Helmholtz equation, which is the seismic imaging, and the inverse radiative transfer, which is medical imaging, the CT, and the inverse diffusion equation, which is the Calderon problem, should be the same problem as well. So you would ask why I care. One reason that got me into this is purely just intellectual curiosity. I find it so uncomfortable that the same physical system using different phenomena, different applications get different descriptions. And there's some practical reasoning behind it as well. Suppose you ask a geophysicist, they would tell you that this inverse problem is severely ill-posed, in the sense that if your detector is not precise enough, the reconstruction is very, very bad. And you go to remote sensing, the same thing happens. If you have a little bit of perturbation in your measurement, the reconstruction is also very bad. But if you go to a doctor, the doctor would show you this picture and say, hey, that's a very beautiful picture. It's a well-posed problem. So now the question is, the same problem posed at different regions, posed at different scales, they have vastly different stability, and I would like to understand how the stability either deteriorate or increasing. Hopefully that tells us how to design equipment later on. So I understand that this workshop is on quantum physics, so let me try to fit my quota for the quantum dynamics as well. I do have one very small piece of work. I shouldn't say that I solved the problem, but I do have one small piece of work that is to link the inverse Schrodinger versus the inverse Newton. So let's get that done first before we move on to the light propagation. So over here, we have the Schrodinger equation. You have the Schrodinger equation, and I prescribe you the initial data, and you run the system, and after some time, you detect the state. And then we have the Newtonsecond law. Initially, you give me one electron, for example, located at a certain location, equipped with certain velocity, and you let the electrons run, and after some certain time, you measure the location and the speed of these electrons. So I claim these two systems are the same systems if this epsilon or rescale Planck constant is regarded as small. So there are many choices mathematically. You can do WKB expansion, you can do Gaussian beam expansion, etc. And the tool that I'm comfortable with is the so-called Wigner transform. So how to do Wigner transform? You have the Schrodinger equation, and I define this very complicated function. This complicated function, let's forget about the details, but nevertheless, this new transformed function, it not only depends on time and space as the Schrodinger equation does, but also depends on the velocity. So this is a function that lives on the phase space, not only the physical space. Suppose your original size satisfies the Schrodinger equation. I claim the Wigner transform satisfies this equation. This equation looks simple, but I'm hiding all the secrets in this operator. It's a very complicated integral. However, as epsilon goes to 0, formally you can derive that this operator somehow converge to a very simple operator as well. So now we have one equation with time derivative balancing with 1 and 2 terms. The first term tells you that x dot equals to v. So particle moves with velocity v. The second term tells you that v dot equals to gradient of v, gradient of potential. So that's Newtonsecond law. So we derive the Wigner equation from the Schrodinger equation, and we find out that as epsilon goes to 0, this exactly covers the Newtonsecond law. So that's one way to explain that, well, Schrodinger and Newton, they are truly the same system. Now we are in the inverse setting. The inverse setting is, I tell you the initial data, I also measure the final state. Can I reconstruct the potential? The same story for the Newton. I tell you the initial point of the particle. I tell you after a certain time where the particle is. Can I use this two initial and final time the state to reconstruct the potential over here? Previously, we had said these two systems are the same, so potentially the inverse problem is the same as well. I cannot say that yet. However, I can say that at least in the linearized setting, these two problems are the same. So we assume that, so the so-called linearized setting is the following. We assume that the potential is a summation of two components, some background potential that you know ahead of time, and some fluctuation term. And I assume that the fluctuation term is very, very small. So in this regime, the inverse problem can be reformulated into an integral form. So this v tilde is something that you want to recover. And what you can do is to make the measurement. You project this v tilde onto a function that equals to the data. There are two sources to determine this data. You can tell me what kind of initial data to give you. And you can also tell me at which location you take the measurement. So there, yes, please.
Sorry, when you say it's the fluctuating term, is that changing in time or just slowly varying in space?
We assume it's time independent. Yeah, sorry, yes. Yeah. So there are two things in this data. You tell me what kind of where in this initial data you care, and we also tell after some certain time where do you put the detectors. So there are 2 degrees of freedom in the data. So that's indicated by this 2 index. Associated with this 2 index, we have this representative term also associated with 2 index. So what is happening is you tune this f, you also tune this g, you have a class of functions. This class of functions taking the inner product of the things that you want to reconstruct equals to the data on the right-hand side. So suppose this representative function, this whole class of function spans out, let's say, L2 function space, then we can claim that v tilde is unique in this L2 function space. Okay. So in this inverse setting, what is the representative for the Schrodinger and what is the representative for the Newtonsecond law? So we did a bunch of derivation and we find out that the representative for the Schrodinger is this integral operator. This phi solves the forward Schrodinger equation with some initial data. And this psi solves the inverting Schrodinger equation with some final data. You multiply them together, taking the integral, and that's your representative function. Similarly, for the Newton-second law or the Liouville system, you solve f using the initial data, you solve g using the final data, but you have the representative function as well. They look very, very different. However, I claim they are equivalent when epsilon goes to 0. Once again, through this Wigner transform tool. So let's perform the Wigner transform of phi and the Wigner transform of psi. I can derive the Wignerized Schrodinger representative. It looks very, very ugly. However, once again, we said epsilon goes to 0. As you can probably see, that this term basically looks like, well, as epsilon goes to 0, it's basically the velocity derivative of this f. You put the velocity derivative of f, that's over here. And then this Fourier transform essentially gives you the x derivative of the whole thing. But nevertheless, the bottom line is we have in the linearized setting, we have the linearized Schrodinger inverse and linearized the Newtonsecond law, and we have this representative function. The representative function converge from one to another. That is basically saying that the inverse problems are equivalent to each other. So if one thing is unique, the other thing also gives you the unique solution as well. We did some numerical simulation. So over here, these are two representative functions. We computed as epsilon gradually goes smaller and smaller. As you can see, all this gradually approach to the representative function is suggested by the Newtonsecond law. Similarly over here. And then we compose all the representative functions, formulate a whole list of the functions, and we perform the singular value decomposition to select the most representative ones. And this is the leading mode, and I believe this is the third mode. And we find out as epsilon goes smaller and smaller and smaller, you do converge to the representative from the Hilbert system. Similarly here. So unfortunately, at this moment, I cannot say more. For example, I cannot really say what would happen if you truly tackle the nonlinear inverse problem. A difficulty over there is I can't even find the literature for inverse Schrodinger system. There are literature about inverse Schrodinger, but it's usually time independent. Another reason is intellectually I'm satisfied. I think this is a moment that we need to integrate some real practical setting. So I'm fortunate to be involved in here, so I can probably ask the chemists in the audience, what are the problems that you care that is in the inverse setting? Okay, so the rest of the talk may not have too much relation with the quantum, but I promise to be entertaining. Yes, please.
So we can't measure the Schrodinger, the wave function. We only have access to observables.
Yeah, that's true.
So
yeah.
how does that affect your analysis? Because we see even we see also the
That's a good point. I don't know. However, in the limit, it's basically the classical setting, right? If you're in the classical setting, you can measure the location and the velocity of the particle. Then you can perform the inverse. Yeah. For Planck constant that is non-zero, I don't know. Yeah.
The technique is based on Wigner transform, which is basically a shifted density matrix.
Right, that's true.
Yeah, to some extent. Sketching.
You often talk about particle, but like you're propagating some type of neutral equation. So you're not making any restriction. Your phase space density can be arbitrarily complicated. Is that correct?
That's true. Yeah.
But there's no problem that occurs when sometimes you have two classical stationary action paths that are consistent with a single quantum mechanical propagation. That doesn't pose a problem.
I'm not sure. Can you repeat that again?
Well, I mean, sometimes you say the classical limit is this, you can take it as a stationary point of the quantum path integral, and sometimes there are two stationary paths, like in a double slit experiment. And I assume that doesn't pose a problem. Is that right?
I should mention this tool, Wigner transform. This tool by passing the limit from the Schrodinger to the Newton, there is strong assumption on the potential term actually. I'm not this potential term now. I'm assuming it's non-degenerate and it's smooth and everything. So if your particle has interaction with each other, I actually don't know how to deal with them. Yeah.
I can see with some connection to chemical problems, but there is one thing for chemical. So electrons are fermions. How does the Pauli principle? So it's not only epsilon, which there's a Schrödinger equation for the Newton equation, but it's also the Pauli principle. Can you take care of this? So the symmetry of the wave function.
A quick answer is I don't know. Yeah. My background is pretty weak in understanding the chemist. Yeah. Maybe like I can consult you at a later time. Yeah.
Sorry, the last question.
Yes, please.
Why you choose to map, because it's beautiful work, but why you choose to map the Schrödinger equation into the Newton equation, where the two objects are physically quite different? One is a wave function, and the other are what should be observable, let's say, in the classical limit.
Yeah.
And not, for instance, the Liouville von Neumann equation for the density matrix in quantum system to the density Liouville equation for classical mechanics. This should be maybe more straightforward, because are two objects which has the same interpretation from the physical point of view.
Oh,
you think you can apply this method?
Oh, I think so. I think so. So I do this because this is my background. I feel comfortable doing this. But if asymptotic analysis can be applied in using the limits that you are saying.
That's because they are exactly the same equation, essentially. They phrase the different contexts, quantum, and this for the same object. So probably it's easier to connect. Just.
Yeah, it could be. It could be. I don't have that background. Yeah. Okay, let's start the entertaining part. So radiative transfer or the medical imaging versus the diffusion equation. So this is one of the pictures that I really like. So if you think about the light propagation, there are different descriptions. You go to the atmospheric scientist, and they tell you that light propagates using the radiative transfer. The sun shines up the earth, some of the light goes through, some of the light gets bounced around. So you write down the equation with two terms. This term tells you x dot equals to v, particles go straight. And this term tells you that the particles get bounced around. Using the sigma tells you the thickness of the cloud. So that's their description. And another description was hinted 500 years ago by Da Vinci. He was saying if you move an object 5 times away from you, this object looks 5 times bluer. So the mountain at the background is very blue. So the blue, he was basically hinting that the blue light, in the entire spectrum of light, blue light is the diffusest one. So the diffusion equation is a way to go. So now the question is, you have two types of equations. What's your relation? And we believe, at least during the past 50 years or so, we believe that the connection between these two equations lies in sending the Newton number goes to 0. Newton number is this number that tells you how often the photon get oscillating before it exits the domain of interest. So in this rule, for example, from one point to the other point, the particles, the photons will bounce around a lot. That means the Newton number is very, very small. So suppose I put the Newton number over here and then expand my solution in terms of Newton number and put it back into this equation, perform this order by order reduction. I find out that in the limit, when Newton number is extremely small, the distribution function of space and velocity becomes degenerate. You have one function on the velocity domain that can be explicitly written down, and the function on the spatial domain satisfies the diffusion equation. So that's basically the connection between the radiative transfer versus the diffusion. Okay, so how does it affect the inverse problem? You go to a hospital, and the doctor will order an X-ray. An X-ray picture is very, very sharp. You can see all the details of your bone. Or the doctor doesn't want to harm you. We all know that X-ray is harmful. If the doctor does not want to harm you, the doctor may tell you that go to the so-called infrared some equipment to get a picture. And this is what you get. It's very, very blurred. So what happens is the underlying mathematical description of optical tomography uses the radiative transfer equation as a forward model. But over here, the Calderon problem uses the diffusion equation as a forward model.
Can I ask a question?
Yes.
Is it like also how physicists think about this, the different stability? I thought it's just a wavelength thing.
Yes, it is. It is.
But if it's a wavelength thing, it's a lot more continuous. rather than there is this qualitative difference between the Lipschitz stability and the logarithmic.
That's what I'm getting. That's what I'm getting at. Yeah, thank you. So suppose you use X-ray or use a high-frequency wave, high-frequency light. The operator that we define is the so-called albedo operator. You shine the laser light in, and you detect the laser light out. So you use this information to reconstruct the picture. And we prove it's Lipschitz stable in the sense that you perturb this data by a little bit, the perturbation linearly get affected in your reconstruction. So they can tell apart my hand with respect to your hand, for example. If you use Calderon problem, however, over here we define the operator called the albedo, the directionally to normal map. So you tell me the incoming light source and tell you the flux of the light going out. This is proved to be logly U-post in the sense that you perturb the data by a little bit, the reconstruction can be hugely different. So this bothers me. The radiative transfer is asymptotically equivalent to the diffusion. And you can also prove that the albedo operator and D2N map is asymptotically equivalent, but somehow one reconstruction is stable, the other reconstruction is unstable. And I would like to understand what happens in this limit. How does the stability deteriorate when your standard Newton number goes to 0? So some intuition. To build up some intuition, I just performed this very simple 1D example. This media is a Gaussian bump. The only thing that you can change is the height of this Gaussian. So there's a reference. Let me set it to be 0, and I perturb the height of the Gaussian to be positive or to be negative. And I look at the perturbation in data. So all this perturbation in data get linearly affected. However, for big Newton number, when your photon don't scatter, for big Newton number, you perturb your hand by a little bit. The perturbation in the data is huge. So you can really see the data is sensitive to the hand. In the small Newton number region, when you send the light that is basically this light, basically this light, it doesn't really tell my information on my hand. If that is the case, you have the Newton number being very, very small. You perturb your media by quite a lot. The data only sense it by a little bit. So we know that this Lipschitz stability should have the reflection, should have some kind of dependence on the Newton number. The same story happens in 2D as well. So we have the following proof. We prove that over here we have the Lipschitz stability, we have the linear dependence, but over here we have the log U-postness. Although we cannot reconstruct the log U-post, we at least prove that the Lipschitz constant is exponentially bad. So as Newton number goes to 0, smaller and smaller, this Lipschitz constant is going to blow up. So it is a continuous effect. Yeah. So this is some numerical evidence. So this is a linear reflection, and the constant is exponentially blowing up as Newton number goes to 0. So another side of the story is radiative transfer is the same as Maxwell equation. So that's a wave-particle duality. We can understand light as photons, and we can understand light as waves. So when you think about light as waves, we write down the Maxwell equation, or the simplified version is the Helmholtz equation. You describe the wave, and this is the picture that you get. You send the waves in, you detect the waves out. Oh, yes, please.
How does the exponential growth boils down to a logarithmic?
I don't know.
There's some.
Yeah, there's something to do there. Yeah.
So the exponential is upper bound.
Yes. Yeah. I should also say our exponential. The exponential is the upper bound. The logarithm is sharp though. Yeah. So we don't have the lower bound. Yeah. So when you think about the wave, you have the picture like this. This is from undergrad physics. Or you think about the light as particles. You shine the laser light in, these particles, the photons bounce around, and you detect the image over here. So the same story, I either describe light using the Maxwell equation with this n telling you the reflective index, or I use basically the photon transport equation with this n refractive index tells you how the photon particles change its course. So the wave interpretation and the photon interpretation can also be linked together. once again, using this Wigner transform, suppose I say you solve the Helmholtz equation with k indicating the frequency of the light, and I can prove that its associated Wigner transform satisfies the Wigner equation, and as k goes to infinity, as the frequency goes bigger and bigger and bigger, this f converges to a function that satisfies the Newtonsecond law. So in some sense, we are saying that the photons, as a particle interpretation of light, also satisfy the Newtonsecond law. So the significance of this result was that it links the wave description with a particle description. So it partially answers what Einstein projected a century ago. The Wigner transform is this complicated form that I'd like to remind you of. So I'd like to say that the inverse problem is the same as well. So the inverse scattering, or the Helmholtz equation, the inverse problem is severely ill-posed. So over here, the map that you have is I send the wave in, and the wave is called the incident wave, and I detect the wave out. The detection is called the scatter wave. So the map is the incident to the scatter wave pairs, and I'd like to reconstruct the refractive index. And it is proved to be very bad. Somehow, you go to the Lipschitz limit, you have the radiative transfer of the Newton-second law as a limit. We have the same map. It maps the incoming source to the scattered wave, to the scattered light, and this guy is Lipschitz stable. So that's very strange, right? You change from one description to the other description, the inverse problem changes its stability. So, yes?
I'm not sure I'm following, but this is just a general question, which is, again, when you have particle problems, you have the possibility for chaos, and so that seems relevant to the inverse problem, right? And then when you have these wave equations, which is linear, chaos is not really present in that formulation. So does that pose a problem that you have that sort of particle equations have the presence of chaos in one language and not in the other?
Chaos?
Yeah.
I'm not quite follow what does chaos mean in this setting. Do you mean the
dependence to the initial condition?
Oh, yeah. So the sensitivity of the initial condition gradually comes down as you become the particle. So basically, if you're a particle, there's no uncertainty. You basically get pushed around by the underlying potential.
Maybe you need interactions. So there are no interactions between the particles.
It could be, it could be, yeah.
It's also finite time arrow, is that right?
This is time independent.
Oh,
this is time independent. Yeah. Right. So this is the same question. We have the two different descriptions, although they are equivalent to each other, but somehow using one description you get ill-posedness, and using another description you get the well-posedness. And I'd like to understand why. So this is getting a little bit detailed. If you're looking at the inverse scattering, or if you're a geophysicist, you want to conduct the seismic imaging, the wave or the source that you send in, usually they assume that the source is either the plane wave or the delta Gaussian function, the Green's function. So that is basically mean you either have the concentration of location, you have this point that sends a wave out, or you have the plane wave that tells you the concentration of the velocity. But if you think about the laser light, right? So we have the laser light. The laser light, you can tell me where to put the laser light, and you can also tell me how to orient your laser light. So you can have concentration in both location and velocity. So there's one piece of information that has been lost in seismic imaging. So basically, we're saying this data set is not enough. Yes, please.
This I don't understand. You have a superposition principle, don't you?
Yes.
So
So I can take linear combinations of those delta peaks, say, and plane waves, and build up any x, comma v initial.
Right. You have the uniqueness. You don't have the stability.
Okay.
Different basis function
You said
can.
there's a loss of information.
Right. Probably yes. This is probably a little bit big. So represented on different basis function, you have different conditioning. Yes. They both have unique reconstruction. It's just one is more stable than the other. So we basically decide to enrich or to turn your data set into some concentration in both location and velocity, and we can prove that using this revised modulus of the Helmholtz, we have the same amount of information as using the Newtonsecond law. So both of them are Lipschitz stable. So there's some pictures. So over here is the frequency gradually increase. As you can see, the lower frequency light, it immediately spur out. And as the frequency gets thinner, higher and higher, the beam gets thinner and thinner eventually. So this is a straight line, and over here it bends over because of the refractive index is nonlinear. And this picture is to show that if you have low frequency light, you shine the laser light in, and the light diffuse a lot. So suppose you shine the laser light in a specific location, orienting at a specific direction. There are a lot of directions you can sense the data, and for each direction you have a lot of angles that can sense the data. However, if you make your frequency higher and higher, then I have only one point on the other side of the lake that can sense the data only with specific orientation. So this is the reconstruction. This is the ground truth media, and this is the reconstruction using the concentration both in location and velocity. That's very good, but the standard is U-post, as you can see. It doesn't really reconstruct anything. So that basically explains, or gives one side of the explanation that why the inverse radiative transfer or the inverse Liouville-Newton-second law is a better reconstruction than the inverse Helmholtz. So that basically completes the story. I would like to end my talk with the following argument. So when I started this project, it was purely just for intellectual curiosity. I would like to understand how do you transfer from one system to a different system. There are some practical advantages as well. Besides, potentially, we hope that it can tell the doctors how or what kind of frequency of light should you design for medical imaging or things like that. Another one is for optimization strategies. So you can imagine sending different frequency of light to a hand. You have the same hand, right? So using one frequency to shine my hand and using a different frequency of light to shine my hand, you get different sets of images, but one is more blurred than the other. However, X-ray cause you the harm, so you would like to avoid using X-ray. So there's potentially some kind of combination. You use X-ray on some specific location while the others do not use X-ray. So there potentially bring some from some advantages over there. And since I'm here, I believe there must be some inverse problem from quantum chemistry. I stopped doing this Schrodinger versus Newtonsecond law because I really don't have assessment of what is important problem in quantum chemistry. But I think there must be some, and I would like to hear feedbacks from you guys. Thank you very much.